Hello viewers, in today's session we are going to discuss another important and very conceptual problem from integrals, right? So here we have to evaluate this integral from 0 to 1, and here the integrand is x times 1 minus x raised to 4, and the whole power is 5 over 2, right? So here we have to evaluate this integral using the concept of beta and gamma functions, right? So we'll make use of some important results from beta gamma functions to evaluate this integral. So let us first make the use of substitution method, and then we'll apply the different relations or different concepts from beta gamma functions. So let us start. So let us call this integral as I, and let us make the substitution that is t is equal to x raised to 4. So here I will take t is equal to x raised to 4. Now differentiating t with respect to x, we have dt over dx is equal to the derivative of x raised to 4, and using the power rule for differentiation, we have the derivative of x raised to 4 is 4 times x cube. So now from this relation we have x is equal to t raised to 1 by 4, and taking the value of x is equal to t raised to 1 by 4 over here, we have 4 times, then we have t raised to 1 by 4 raised to 3. So this is 4 times t raised to 3 by 4. So dt over dx is equal to 4 times t raised to 3 by 4. So now dx can be written as dt over 4 times t raised to 3 by 4. So this is equal to 1 by 4 t raised to minus 3 by 4 dt, right? So for dx we can take the value as 1 by 4 t raised to minus 3 by 4 dt. So now here the limits of integration vary from 0 to 1. So let us change the limits accordingly. So when x is equal to 0, which is the lower limit, so we have the value of t as 0 raised to 4. So here I will take x is equal to 0. So t is 0, and when x is equal to 1, 1 is the upper limit. So t is 1 raised to 4, that is simply 1. So when x goes from 0 to 1, t goes from 0 to 1. So now let us rewrite this integral in terms of t. So now I is equal to integral from 0 to 1. For x we can write t raised to 1 by 4, and here we have 1 minus t, and then we have 5 over 2, and for dx we can write 1 by 4 t raised to minus 3 by 4 and dt, right? So now we'll simplify this expression, and we have 1 by 4 outside the integral, and here we have 0 to 1, and here we have t raised to 1 by 4 and t raised to minus 3 by 4. So we have 1 by 4, and here we have minus 3 by 4, and here we have 1 minus t raised to 5 by 2, and this is dt. So now we can write 1 by 4 and 0 to 1, and here we have 1 minus 3 is minus 2 divided by 4, so this is minus half. So we have t raised to minus half, and this is 1 minus t raised to 5 by 2 dt. So our integral I is now 1 over 4 0 to 1, and then we have t raised to minus half, right? Now see, minus half can be written as half minus 1. So here we write half minus 1, and then we have 1 minus t raised to 5 by 2, and 5 by 2 can be written as 7 by 2 minus 1, because 7 by 2 minus 1 is 7 minus 2 over 2, that is 5 over 2. So here we can write 7 over 2 minus 1 dt. So our integral I can now be written like this. So now here let us define the beta function. So the beta function is defined as beta of m comma n as the integral that is 0 to 1 x raised to m minus 1. Then we have 1 minus x raised to n minus 1 dx for m and n greater than 0, right? So now we can see that this integral is similar to this one. So here we are taking the variable x, and here the variable is t. So now if we compare this integral with this one, then this is a beta integral, and the value of m is equal to half, and the value of n is equal to 7 over 2. So this 1 over 2 is our m, and this 7 over 2 is our n, right? So m is half, n is 7 by 2, and this integral is known as the beta function or the beta integral. So we can now write I is equal to 1 by 4, and here we have beta of m comma n. M is half, and n is 7 over 2. So now our aim is to find out the value of this beta function by converting it into a gamma function. So the relation between beta function and gamma function is given by beta m comma n, and we have here gamma of m, then gamma of n divided by gamma of m plus n. So this is an important relation connecting the beta function and gamma function. So here beta of half comma 7 by 2 can now be written in terms of gamma function as gamma of half, then gamma of 7 by 2, and divided by gamma of half plus 7 over 2. So now we have to calculate the values of these three terms. So now I can be written as 1 by 4. Then we have gamma of half. Gamma of half is equal to square root of pi. So here we have square root of pi. Now gamma of 7 by 2 can be expanded, or it can be written in terms of square root of pi by using this relation, that is gamma of n plus 1 is equal to n times gamma of n, right? So gamma of 7 by 2 can be written as gamma of 5 by 2 plus 1. So now we have gamma of 5 by 2 plus 1, so this is our n. So we have gamma of 7 by 2 as 5 by 2 times gamma of 5 by 2. So now gamma of 5 by 2 can further be written by using this relation. So we can now write 3 by 2 plus 1. 5 by 2 is 3 by 2 plus 1. So we have 5 by 2. And then using this relation, now n is 3 by 2. So here we have 3 by 2 times gamma of 3 by 2, and this is 5 times 3 is 15, and here we have 4, and then gamma of 3 by 2 can be written as half plus 1. So again, using this result, we have n is equal to half. So we have 15 by 4 times half and gamma of half, right? So this is now equal to 15 over 8. 4 times 2 is 8, and gamma half is equal to square root of pi, right? So gamma of 7 by 2 is equal to 15 over 8 times square root of pi. So now I is 1 by 4, gamma half is square root of pi, and gamma of 7 by 2 is 15 over 8 times square root of pi, right? And in the denominator we have gamma of half plus 7 by 2. So half plus 7 by 2 is 1 plus 7 over 2, that is 8 over 2, that is 4. So in the denominator we have gamma of 4. So this is gamma of 4. Now using this result, that is gamma of n plus 1 is equal to gamma n factorial, and here gamma of 4 can be written as gamma of 3 plus 1, that is 3 factorial. So 3 factorial is 3 times 2 times 1, that is 6, right? So here n is equal to 3. So in the denominator we have that is 6. So I is now equal to 1 by 4, and gamma of half is square root of pi. Gamma of 7 by 2 is 15 over 8 times square root of pi, and gamma of half plus 7 by 2, that is gamma of 4, that is equal to 6. So now we can simplify this expression. So square root of pi times square root of pi is simply pi, and in the numerator we have 15, and here we have 4 times 8 times 6, right? So now we can cancel 15 and 6. So this is 3 times 5, and this is 3 times 2. So we have 5 pi, and here we have 4 times 8 is 32 times 2, that is 64, right? So the value of this integral is equal to 5 pi over 64. So viewers, the value of this integral I can be obtained by making use of the concept of beta and gamma functions, and the value of this integral is 5 pi divided by 64. Hello viewers, in today's session we are going to discuss another important problem from indefinite integrals, right? So here in this class we are going to evaluate this integral in which we have to find the indefinite integral of this function, that is cosine inverse 1 over x, right? So to evaluate this integral, we'll make use of two important concepts. So the first one is integration by substitution method, and then we'll apply the concept of integration by parts. So let us call this integral as I, right? And here we have cos inverse of 1 over x. So let us make this substitution, that is cos theta is equal to 1 over x, right? So why we have taken this substitution? Because see here our integrand, say f of x is cos inverse 1 over x. Now when we take 1 over x, then we have cos inverse cosine of theta, and from the inverse trigonometric functions we can write cos inverse cos theta is equal to theta. right? So f of x is equal to theta, where cosine theta is equal to 1 over x. So here we can cancel this cosine inverse and cos by definition of the principal value branch of cosine inverse function, right? So we'll make this substitution, and now we can write x is equal to 1 over cos theta, and 1 over cos theta is secant theta. So we have x is equal to secant theta. So now let us differentiate x with respect to theta. So we have dx over d theta is equal to the derivative of secant theta. So the derivative of secant theta is secant theta tan theta. So now the value of dx is equal to secant theta tan theta d theta, right? So now we can rewrite this integral I in terms of this new variable theta. So we can now write integral, and cos inverse 1 over x is equal to theta, and for dx we can now write secant theta tan theta d theta. So now this integral is reduced to this one with the help of this substitution. So now to evaluate this integral, we'll make use of the method of integration by parts, right? So let us first see the formula for integration by parts. Suppose we have two functions of theta, then we can write the product of the two functions u and v, and here we have d theta. So suppose u and v are functions of theta, then the integral of the product of the functions u and v is given by u. We can take u as the first function, then v as the second function. So we can write u multiplied with the integral of v, and then we have integral, then we have the derivative of u with respect to theta, and then here we have the integral v d theta, and then this entire term is integrated with respect to theta. So this is the formula for integration by parts when we have the product of two functions. So now here our integrand is theta times secant theta tan theta. So what we will do, let us frame u and v from this function. So we can take u as say theta, and v as this function that is v, because we know that the integral of secant theta tan theta d theta is equal to secant theta, right? So now taking u as theta and v as secant theta tan theta, we can now substitute the value of u and v in this result. So our integral I now it becomes theta secant theta tangent theta d theta is equal to u is theta, then we have integral v d theta, v is secant theta tan theta d theta minus integral, and then we have the derivative of u with respect to theta, u is theta, and then we have secant theta tan theta d theta, and then here we have d theta. So now this integral is equal to secant theta. So we have theta times secant theta minus integral. The derivative of theta with respect to theta is 1, and the integral secant theta tan theta is equal to secant theta, right? So here we can write secant theta d theta. Now, from the standard results of indefinite integrals, we know that the secant theta, the integral of secant theta is given by a log of sec theta plus tan theta, right? We can also use this result also for integral of secant theta, that is log of tangent of pi by 4 plus theta over 2. So we have two results for the integral of secant theta. So here we'll prefer this result, and we have I is equal to theta secant theta minus the integral secant theta is now equal to a log of secant theta plus tan theta, and here we have the constant of integration as c, because we are dealing with indefinite integrals. So now this result is in terms of theta, but our original integral was in terms of x. So let us convert this result in terms of x by using this result, right? That is x is equal to secant theta. So here for theta, we can write theta is equal to cos inverse of x, because here we have theta, that is cos theta is equal to 1 over x. So theta is cos inverse of 1 over x from this result, right? So here we have cos inverse of 1 over x, and for secant theta we have simply x and minus log, and for secant theta we have x, and for tan theta we can use this standard result from trigonometry, that is 1 plus tan square theta is equal to secant square theta. So tan theta is equal to square root of secant square theta minus 1. So if we take secant theta as x, we have x square minus 1. So for tan theta, we have square root of x square minus 1 plus c, right? So the value of this integral is given by x times cos inverse of 1 over x minus log of x plus square root of x square minus 1 plus c. So for this term, we can use the inverse hyperbolic function, and we know that the inverse hyperbolic function of cos x, that is cos h inverse x, is equal to log of x plus square root of x square minus 1. So the inverse hyperbolic function of cosine x is given by a log of x plus square root of x square minus 1. So here we can replace this log term by the inverse hyperbolic function, and here we have c. So the value of this integral can be taken as this expression or this expression. So viewers, if instead of taking the integral of secant theta as log secant theta plus tan theta, if we would have taken the integral of secant theta d theta as this term, then we would have theta secant theta minus a log of tan of pi by 4 plus theta over 2 plus c, right? And then secant theta is x, and theta is cos inverse of 1 over x minus log tangent of pi by 4 plus half. For theta, we can write cos inverse of 1 over x plus c, right? So in that case, if we would have taken this result, then our the value of this integral would have been x cos inverse 1 over x minus logarithm of tangent of pi by 4 plus half cos inverse 1 over x plus c.